We can start with my very brief introduction. Actually, it's a welcome. Welcome to all of you. It's my pleasure to open this new GGI series of theory lectures by young researchers, and the accent is on by. In fact, this is a new proposal, and I'm confident it will be a success. The program will cover different research topics spanning cosmology, lattice gauge theory, quantum field theory, strings, and mathematical physics. These are the research areas of the proponents of these events. They are our 5 great GGI postdocs. Here they are: Claudio Bonanno. He will get his PhD in Pisa University. Claudio, say hi.
Hi.
Alessio Caddeo.
Hello.
Hello. He will have his PhD in Florence University. Carlo Alberto Cremonini.
Hi, everybody.
He is from Turin or Alessandria? Where did you?
Formally Como, but actually
okay.
In Alessandria.
Okay, north. Just over the north. Matteo Mario.
Hello, everybody, and welcome.
He is already doctor in Lecce. And Rocco Rollo.
Hi, everybody.
Hi, Rocco, with the cats on the shirt. And from GSSI. So thanks to them, we open this new series of lectures. The lectures are live streamed on the YouTube GGI channel and also on Facebook. The chair of the lecture of today is Carlo Alberto, and I leave him the microphone. Thanks for being here.
Thanks, Stefania, for the introduction to this series of lectures, and thanks to all the participants and to Lucrezia, who is the first speaker of the first lecture of this initiative. Lucrezia will talk about a geometric approach to supergravity, and the goal of this series of lectures is to introduce an informal environment where everybody can ask questions freely. So please really feel free to ask a question whenever you want and whatever type of questions you need. I'm sure that Lucrezia will be happy to answer to everything. So, okay, I think we can start. Lucrezia, the stage is yours.
Okay, thank you, Carlo. And thank you, Stefania, for the nice introduction, and to all the organizers for this nice opportunity of giving these lectures. And thank you to all the participants for being here. Let me share the screen. Okay. Now you should see.
Yeah, perfect.
Okay, perfect. And so today, in these lectures, we will see the geometric approach to supergravity. And today I will start with a first review on some key points of pure gravity in the Cartan formalism. First of all, let me give you a quick overview. I will start from the key points of pure gravity in Cartan formalism. And this will be an introduction. Since then, after this, we will move to the group manifold approach to pure gravity. And this because, and I will briefly review the key points of these approaches, and this because, firstly, Cartan introduced a formalism, purely geometrical formalism for gravity theories, which is completely independent of the coordinate frame that is invariant under the group of general coordinate transformations. And after that, which this already allows an interesting geometrical interpretation of gravity theories, and in which we deal with differential forms and so on. But after that, in 1978, we have Niemann and Th-LYR who developed, who further investigate on this approach and developed the so-called group manifold approach, which consists in extending Cartan formalism to the whole group manifold on which the theory is based, that is, on which the Lie algebra value gauge fields lives in the coadjoint multiplet. And so we will review this, and in particular the pure gravity in Cartan formalism, and the way in which this is extended to the Poincaré group manifold. And after that, we will move finally in these 2 days to the geometric approach to supergravity, that is also called the super group manifold approach. And it's also known as the rheonomic approach. And this is a superspace approach. I will first of all quickly review n=1, d=4 supergravity in space-time, since I will give you all the general characteristics of the approach, but I will show them to you in a more explicit way by concentrating on this particularly simple example, that is n=1, d=4 supergravity. Then I will introduce the concept of a superspace and thus the geometric approach to supergravity in superspace. And after that, I will try also to show you some state-of-the-art works in which we apply the geometric approach to supergravity, and also to understand in a better way why it is particularly useful to have this geometric view on supergravity. So now, let me also give you some references. These lectures are mainly based on this first ref, that is the book by Castellani, Ravera and Tre. In which you can find the original formulation of the geometric approach, and essentially in volume 1 and 2, since in volume 1 and 2 of this big blue volume of books, there are 3 volumes. In volume 1, you can find a review of differential forms formalism and also the group manifold approach, and then volume 2 essentially deals with supergravity in the geometric approach. So the complete original formulation, and after that application to the development of supergravity theories in different dimensions. Then there is also this other review, which is much shorter, and but it's a very nice review by Riccardo Daura again. And I can give you the archive number, that is 2005 13593. Okay, and this is a review which appeared in an interesting, nice book on Th-LYR, and there you can find details on the geometric approach to supergravity and applications. Then there is also my PhD thesis, if you wish. This is the archive number, and there you can find a review. Oh, sorry. There you can find a review of the geometric approach to supergravity, and moreover, you can also find some recent applications and and a part which deals with free differential algebras, which is an extension of the framework of the Maurer-Cartan equations for describing the vacuum of supergravity theory, in the case in which you have higher degree forms, that is when you deal with higher dimensional theories. And we will see how Maurer-Cartan equations are important in this approach, in the group manifold approach, and also in the supergroup manifold approach. And so there you can find an extension. If we will have time tomorrow, I think we will also have a brief overview on this topic. And then there are several other books in which other papers in which you can find short review of some parts, key points of the geometric and the rheonomic approach. Let me mention this one in particular, which is by Laura Andranopoli. And Riccardo D'Aurea. And the archive number is this one. And in particular, here you can find a review of some of the Lagrangian construction in the geometric framework in the appendix. And I think that this is a nice paper, since it deals with the construction of particular supergravity models in the presence of a non-trivial space-time boundary, that is when the fields do not vanish asymptotically at infinity. And so they found a way in which supersymmetry in this particular framework can be restored by implementing the geometric approach to supergravity. So you have completely geometrical insights also on this issue. And we nowadays we are currently exploiting the approach of this paper, Theories with Boundary, to study holography with asymptotically untitled Sitter spaces. So this is also very interesting from this point of view to deal with state-of-the-art papers. Okay, so we can start from those preliminaries on the key, just quickly reviewing the key points of gravity in Cartan formalism. So Cartan formalism. And here, let me focus on the equal for simplicity. Of course, this can extend to any dimensions. So I will focus on pure gravity in 4 dimensions. And here, what we have is that the theory is described in terms of differential forms. We have the spin connection, omega AB, and the field bane, which are one-form gauge fields. And they are part of the adjoint multiplet mu A, where A runs from 1 to 10. And this is of the adjoint multiplet of the Poincaré algebra. And we have that the index A is decomposed with respect to the Lorentz subgroup. So we have Lorentz subgroup that is SO13, and the index A that is decomposed into ABA, and thus we can write mu A equal to omega AB A, where A, B run from 0 to 3. And this span a basis of the cotangent plane of the Poincaré group. And the difference between the essential, let's say, difference between the spin connection and the field bane is the fact that the field bane, which we can write as the A, we can expand it on the basis of differential forms, so the A mu, the X mu. We have that the field bane propagates while the spin connection does not. And let me also write the spin connection on the basis, expanded along the basis, the differential form basis. And so, as a consequence of this fact, in particular in Riemannian geometry, what we have is that the curvature of the field band, that is the torsion, is a torsion to form, must vanish. And this implies in particular that the spin connection is completely given in terms of the field band and its derivatives. And this implies what is called the factorization hypothesis. Which essentially states that omega AB and the field band are on a principal fiber bundle that we can write it as M4 over SO13, where SO13 is the Lorentz group, and where M4 is the base space, and this is the physical space-time. And in the vacuum configuration, what we have is a coset base space G over SO13, where in particular, in this case, G is ISO13. And so this the factorization hypothesis consists in saying that we have a principal fiber bundle with this structure. In this first part of the review, I will also show you how we get factorization and the horizontality of the curvatures with respect to the Lorentz directions. And after that, in supergravity, and in gravity also, what we usually do is assuming factorization and horizontality of the curvatures from the very beginning, since we know that we are dealing with H invariant. Let's call H is the fiber SO13. We are dealing with H invariant Lagrangians, and so we directly assume factorization and horizontality from the very beginning. And so after having seen this geometrical framework, now we can say what is the group manifold approach. And it is based on trying to construct a gravity theory directly on the group manifold. Group manifold G, which is the whole ISO 13 in our case. And so what we do is consider the fields of the theory, and writing for these fields, for the one-form fields, the Maurer-Cartan equation for the one-forms in the coadjoint representation of the group. And the Maurer-Cartan equation describes the vacuum of the theory, and they are dual to the Lie algebra describing the theory, in the sense that the D2 closure of the Maurer-Cartan equation is equivalent to the Jacobi identities for the Lie algebra structure. And then we have to go out of the vacuum for constructing a dynamical theory. And so what happens out of the vacuum is that we have that the one forms are spanning a basis on the cotangent plane, on the cotangent space of the group manifold G, and they become dynamical. And so we introduce the curvatures, the non-vanishing curvatures, which are the field strands of the dynamical fields. So field strands of the dynamical fields. And in this framework, what we do for building a Lagrangian, a gravitational Lagrangian in generating D dimensions, is writing a Lagrangian that is a D form. So the Lagrangian here is a D form. And Lorentz invariance of the Lagrangian can be retrieved from the equation of motion, even if the Lagrangian has to be integrated on the whole group manifold. And even if so the dimension of the group are greater than the degree D of the Lagrangian. And so here we can, this can be done because we can consistently integrate on a submanifold this deformed Lagrangian. And this can be consistently performed as a result of the invariance under the group of general coordinate transformation. So the group of general coordinate. And what happens with the equation of motion when we write the Lagrangian, we derive the equation of motion. We have that the equation of motion is horizontality of the curvatures in the Lorentz directions. And this, and from this follows that we have the factorization of the Lorentz parameters. And we will see this in more details in a while. Then let me also anticipate that all what we have seen till now can be extended to graded groups. That is two supergroups. And this is particularly important since it allows a geometrical interpretation of supersymmetry. And so when we build supergravity theories, we have to deal with fermionic irreducible representation and with supersymmetry. And in this geometric approach, we can have some geometrical insights on supersymmetry. So geometrical interpretation of supersymmetry. And in particular, we will see that with the rheonomic geometric approach to supergravity in superspace, we will be able to have an understanding of supergravity in superspace very similar to the one, analogous to the one that we have for pure gravity on space-time. And we will consider, for simplicity, let me also mention this, that for the case of supergroups and of supergravity, we will consider the simple example of n equal 1, d equal 4, pure supergravity. That is in the absence of any internal scaling in the Lagrangian. In a very simple model where the coadjoint multiplet is given just by the spin connection, the Vierbein, and psi alpha with alpha that goes, from 1 to 4. And again, AB that goes from 0 to 3, where this psi alpha is the gravitino. And it's also called the fermionic Vierbein, and it's a Majorana spinor one form. And we will, therefore, we will have in our theory different type of transformations. We will have a translation, Lorentz transformation, as in pure gravity, but also we will have supersymmetry transformation. In particular, we will have odd fermionic Grassmann parameters that we will call the theta alpha. And so we will have for the whole supergroup manifold dependence on, we will have all these coordinates related to translation, Lorentz, and fermionic Grassmannian ones. And then we will see that we will be able to deal with Lorentz factorization in the same way that we will do now for pure gravity. But on the other hand, for supersymmetry, for the fermionic parameters and for the fermionic directions, we will have to work in a different way. And so we have also said that this is an approach when we study supergravity theory on superspace. And so let me also mention that the superspace, and I will in any case review the concept of superspace, is spanned by the super Vierbein, A psi alpha, since this will be the basis while Lorentz will be factorized. And so from the superspace equations of motion, we will get horizontality of the curvatures. And so from the equation of motion, we will have horizontality. Of the curvatures with respect to Lorentz, but then some constraints. On the super curvatures, let me call them super curvatures. And when I will discuss supergravity, I will also sometimes use curvatures, but I will intend super curvatures in the fermionic direction. So we will have some constraints on the supercurvatures in the fermionic directions. And these will in particular allow to restrict the theory from the whole superspace to space-time. And this is important since we know that there are different approaches to supergravity in superspace, different superspace approaches, and they are different, but they have in common the fact that at the end there is some constraints to be imposed. For instance, here on the supercurvatures components, as we will see, but on another example on the fields, in order for not to have some spurious extra degrees of freedom in the theory, and to have the same physical content of the theory on space-time. And this, as we will see in the following, we will see that in the rheonomic approach, this is implemented really geometrically in a very nice way. So these, in particular, we will see that the components along the fermionic directions of the curvatures will be given in what we call, in fact, rheonomy. Will fulfill the rheonomy, that is in a few words that these components, which we will call outer components, will be expressed linearly, algebraically and linearly, as tensor combinations of the inner ones. So in terms of inner, on the cotangent plane of the space-time manifolds. And so this will allow a geometric interpretation of supersymmetry. And in particular, we will see that the point is that the superspace diffeomorphism, these diffeomorphisms in superspace will be seen as supersymmetry transformation on space-time. And these, we can see that we can say that these are the main features of the rheonomic approach, and we will see all of these in detail. So now let me start from pure gravity, as we have said before, from pure gravity. And we will see all what I have mentioned before explicitly now. So we will start from pure gravity in Cartan formalism. And to its extension to the Poincaré group manifold. So now what we have is that, as we have already mentioned, we have the gauge fields, which can be written in terms of differential forms. And these differential forms are dual to the generators of the Lie algebra. So in this case, they are dual to the generators of the Lie algebra associated with the Poincaré group ISO 13. So let me write ISO 13, where the Lorentz subgroup is SO 13. Then we can write the curvatures. That is, we go out of the vacuum. What we will have, we would have in vacuum is the mu plus 1/2 C A B C B wedge. You see where this wedge is the wedge product between differential forms. Mu A, we have already said that it is omega AB dA. And in vacuum, we have that this is equal 0. These are the structure constants of the algebra. But now we want to go out of the vacuum. So we introduced and define non-vanishing curvatures in this way. And in particular, then we can split the index A with respect to the Lorentz decomposition. So we can write the field strength, the Lorentz field strength, that is the Lorentz curvature for the spin connection. It is RAB, defined as d omega AB minus omega AC omega CB. Sometimes I will omit this wedge product between differential forms for being a little bit more quick. And here I put a minus sign because of conventions, which are frequently different in the literature. And I'm used to put a minus sign. But in any case, you can redefine the spin connection, and then you will also get another minus sign in the curvatures, and you can define the Lorentz curvature with d omega plus omega omega. This is just a matter of convention. This is the Lorentz curvature. And then we have the torsion that we call TA, which is defined as the dBA minus omega AB wedge dB. And this is the torsion. And these are, let's say, the curvature, the field strength associated with of the field length. Then what we can do is expand this curvature along the Vierbein basis, and this means writing RAB is equal 1/2. Also, this factor 1/2 is a kind of matter of convention, but let me put it here. Okay. In this way, we expand this two form along the basis of two form along the Vierbein, and this is the Riemann tensor in Lorentz indices. And of course, one can write RAB mu nu, and that is equal 1/2 RABCD VC mu VD nu, in order to get it in components. It's just a matter of expanding along the basis, the differential basis dx mu. And then we can write the Bianchi identities obeyed, fulfilled by these curvatures that are d RAB equals 0 and dt A plus RAB will be equal 0 respectively. And in this first part, we will not use them a lot, but they will be important in the geometric approach, since I will, in supergravity, since I will show you that actually there you can, the Bianchi identities will not be identities anymore. They will be kind of relations between the outer and the inner components of curvatures, and we will see also what I mean with these. And this is particularly relevant since we will get the same information that essentially we can obtain from the study of a theory with Lagrangian formulation from the Bianchi, from the study of the Bianchi identities sector by sector along fermionic and bosonic direction of superspace. And what is usually done at the end is using both these approaches together, just because calculation can be very cumbersome, but you can build the Lagrangian and then get insights from Bianchi identities and vice versa to be as complete as possible. D here is the Lorentz covariant derivative, so let me write it schematically like the derivative, the ordinary derivative minus the spin connection, and this will be Lorentz covariant derivative. Okay, then after that we can write finally the gravitational Lagrangian, the Cartan gravitational Lagrangian, that is a four form, and it's RAB C BC D epsilon A BCD, where epsilon A BCD is the Levi-Civita tensor. This Lagrangian is invariant under diffeomorphisms, and what we have is that formally it coincides with the Einstein-Hilbert Lagrangian. This is the Cartan Lagrangian, and it coincides with the Einstein-Hilbert Lagrangian given in terms of the metric and of the Levi-Civita connection. So in the original Cartan construction, we had omega AB and VA, which depend only on space-time coordinates, and the dependence of Lorentz on Lorentz directions is factorized. Thus, the total space is a principal fiber bundle, as we have anticipated before, M4 over H, with H being SO13. And now we have to see what happens for the same theory, but in the case of the group manifold approach. Here, let me just say that we can also write the action in this way as the integral over N4 of RAB with D epsilon ABCD, where K is square root of 8 pi G and G is the gravitational constant. And so the properties of these theories is that the Lagrangian is equivalent to the Einstein inverse Lagrangian. We have explicit Lorentz invariance, which allows to introduce in particular spinors in the framework of general relativity. That is the way in which we introduce, in fact, spinors. And in word index, what one would have is tensors that transforms under GL4R, and spinors that are in the SO13 representation and can be coupled in these formalisms where we have that the SO13 Lorentz covariant derivative is there. Then let me also mention that this is a first order Lagrangian, in the sense that the spin connection and the field band are considered off-shell independent. And moreover, it is a geometrical Lagrangian, and since it involves the Einstein term, it is built just in terms of differential forms and of the wedge product among them, and thus is uniquely determined. From the study of the equations of motion of the Lagrangian, we get, by studying the variation of the action with respect to the spin connection, we get dc epsilon A B C D equals 0. And from the variation with respect to the field band, we get the Lorentz curvature, the epsilon A B C D equals 0. And we will see this can be expanded along the field band, and then we will see that this implies that the torsion is 0, while this other one will give the Einstein equation. And so, in particular, what we now we can say something about this the invariances of the Lagrangian. So it is invariant under under the group of general coordinator transformation and under local Lorentz transformations. And so even if all the fields are valued in the Poincaré group, the action is invariant only with respect to the subgroup of local Lorentz transformation. And this can be seen by studying the infinitesimal action of the Poincaré group on omega AB and on the field band. We can write the parameter epsilon A in this way, splitting with respect to Lorentz indices A as usual, where this is the infinitesimal Lorentz transformation, while this other one is the infinitesimal translation parameter. And then we write a gauge transformation, the whole gauge transformation with respect to the group as delta mu A equal to the derivative of epsilon A, where this derivative now is the Poincaré gauge covariant differential, the whole differential. And then we can decompose this coadjoint index A in the indices of the Lorentz subgroup and write therefore the gauge transformation for the spin connection, which is the epsilon AB, and those for the field bin. It is the epsilon A plus epsilon AB B. And the Lagrangian is invariant under Lorentz transformation, but not under local translation. And so this is also the reason why when we work in the group manifold approach, we don't say that we have a gauge theory for some group, let's say. Also, if sometimes this is commonly said in the literature, this is actually not true, in the sense that, okay, you can refer to something that is invariant under diffeomorphisms as a gauge theory when you talk about gravitational theories, but what actually happens is that the theory is just invariant under diffeomorphisms, but not under local translations.
Sorry, Lucrezia. Sorry for the interruption. There is a question in the chat. Please, Angelo, feel free to open your microphone and ask the question freely.
Okay, thank you. Lucrezia, what kind of variational principle are you using here? Because the vierbeins are dynamical fields?
Yes. Yes, exactly.
So I'm led to think that are you using Palatine or not?
I'm using Palatine. Yes, is when you consider the vierbein and the connection as independent a priori. Yes, precisely.
Okay,
and
thank
that's
you.
in fact I'm varying with respect to the connection and the vierbein. Yes, I call it the first order formalism, since they are considered as independent of shell independent a priori. Then from the equations of motion, okay, as I will write now, we see that the spin connection is given in terms of the vierbein and its derivatives. But yes, they are independent, and you can just translate really just by projecting along the basis of differential forms. You can see that the results is precisely the same that you get when you consider Palatini formalism, and you vary with respect to the metric and the affine the connection. So yes, it's Palatini variation in those terms. Okay.
Thank you.
So we can now see what happens from the study of the solutions of the equation of motion. And in fact, from the variation with respect to the spin connection, we obtain this first equation. This is from this variation. And then we can expand, and this is also for let you see how we get the usual equation to which we are used to, most frequently used to. We expand T A in this way, T A B C will be C along the vierbein basis. Then by plugging this expression back into this equation, we get that the trace of these components along the vierbein basis are, this trace is 0. And then this will imply that TABC is equal 0. That is that the torsion is 0. But then from the definition of the torsion that we have written at the beginning, we can see that this means that the derivative of the Vierbein minus omega AB Vierbein is equal to 0. And then we can expand this final relation in terms of the differentials, and what we get is this relation between the derivative of the Vierbein, anti-symmetrizing mu nu, since we are expanding, recall, along this basis in which we have differential forms, and so this is anti-symmetric in mu nu, and then equal to omega AB mu B. And then manipulating this expression, considering the fact that the spin connection is defined to have the Lorentz indices AB anti-symmetric, we can write all the combination for the spin connection and obtain the final expression for the spin connection in terms of the Vierbein and its derivatives. And this is to come back also to the point of the question. This is equivalent, okay, let's say, yes, equivalent to saying that the connection is given in terms of the metric and its derivatives in coordinate formalism. And so what is interesting is the fact that we have varied the action with respect to the spin connection, and from precisely this equation, which is the vanishing of the torsion, we have obtained the expression for the spin connection in terms of the Vierbein and its derivatives. And now we can analyze the second equation of motion that we have written before. So the second equation was RAB C epsilon ABCD equals 0. So varying with respect to the Vierbein. And then we can expand again RAB along the Vierbeins in this way. And then plug this expansion into back into the equation of motion, and what we get is precisely the Einstein equations. And I'm using Carlo letters to identify the Ricci tensor and the scalar curvature, respectively. So this is the Ricci tensor, RAB, defined as RAMBM, while this is the scalar curvature. The Ricci scalar are defined as RAA. So the contraction of the Ricci tensor. And now that we have seen the theory, the complete theory in the Cartan formalism, we can extend it from G over H, let's say, to the whole group manifold G. So we start from, we have already said that we have G, that is the Poincaré, so extend to group manifold G. So we have G, that is the Poincaré group, and H, that is Lorentz. We have the vacuum configuration. It's a fiber bundle ISO 13 over SO 13. And then for a general configuration, so in a vacuum, we have a fiber bundle structure ISO 13 SO13. While for a general configuration, we have that the gauge fields mu A, omega AB, VA of the Cartan-Einstein-Lagrangian live on a fiber bundle that is now M for H, where H is always the SO13 fiber, while M4 is the base space, and we consider M4 as we can see it as a deformation of ISO 13, that is what is necessary to go out of the vacuum. So deformation of ISO 13. And in an equivalent way to this one, we can say that the G, that the manifold G is deformed into G tilde, which is where we have dynamical fields. And this is also sometimes referred to as a soft group manifold. And I will try to recall from now on to put, since we will transform, we will move to the dynamical frame, so we will consider always this soft group manifold. I will try to remember to put the tilde, but in any case, I will consider this soft group manifold. And also we have that now the fiber bundle structure is G tilde over H. Then we can assume that the fields, the spin connection and the field, and so mu A defined on the whole group manifold ISO 13 from the beginning allows a factorization of the Lorentz coordinate. And on the other hand, if we start from the whole group manifold, so where G is the complete ISO 13, and we do not assume factorization of the Lorentz coordinate, we consider it absent, and we have that the mu. Now I will just start from this point and show how factorization emerged, just to let you know what happens in this formalism, and then in supergravity I would also always assume factorization of Lorentz coordinates. So if we consider the whole group, we have that omega AB and the field, but depends on the full set of of 10-dimensional group coordinate. That is on, let me write x mu for translations and epsilon mu nu. Y mu nu for Lorentz transformation of SO13. And then we can see mu A as a set of fielding which span a local reference frame on this 10-dimensional cotangent plane at each point of the fiber bundle of G tilde over H. And so essentially what we have, let me try to give you a graphic representation, is this. This is G tilde, and this is a soft and kind of soft group manifold. And here we have in this point a cotangent plane, which is spanned by let's write mu B and mu A, where mu A is the complete set of fielding on G tilde. And this is the situation right now. Now we can consider the Lagrangian that we have written before. Let me write it again. is R, A, B, C, D, epsilon A, B, C, D, where both the field band and the curvatures are not factorized, and these will depend on the full set of G coordinates that are x mu and y mu nu. So we have that the Lagrangian, if we look at it, we can see that the Lagrangian is formally the same, but the problem now is actually to write the action, since we have to integrate the Lagrangian over a d-dimensional space, the d-dimensional space of G tilde, and in the case of Poincaré, this d is equal 10 for Poincaré. So there is a way out, but there is a way out, and that is to embed the four-dimensional space-time on as a four-dimensional hypersurface M4 in G tilde. So this will embed space-time as a hypersurface M4 in G tilde. And however, we have to recall that we are considering a variational principle to study the equations of motion of the theory. So we have that M4 is now a dynamical variable. It will appear in the variational principle, and so it is subject to variation, and this can spoil somehow geometricity. And so here the crucial point, the crucial observations is that one can safely ignore the variation of M4, since any variation of M4 can be compensated by a change of coordinates xm. So let me write ignore variation of M4, since it can be compensated by change of coordinate xm equal x mu epsilon mu, sorry, y mu in G tilde, under which the geometric Lagrangian is invariant. And so we can safely write geometric theory, the theory on the group manifold in a geometric way, and also study the variational principle. There are some further comments on geometricity of this theory, which are rather important, and is the fact that when we say that a Lagrangian is geometric, we mean that it is written in terms of differential forms, wedge product among them, and the differential operator d, such that the square is equal 0. And we have to exclude the Hodge duality operator. And this is important. Let me. Hodge duality is excluded. And this is because of we are considering the integration over an hypersurface that can be chosen in an arbitrary way due to invariance under diffeomorphism, and thus the equation of motion hold on the whole group manifold G tilde. And instead, if we allow for Hodge duality to be present, this would give a dependence on the hypersurface M4 and on its matrix. And for instance, when we will have to add vectors and scalars, the kinetic terms, and we will see this in the supergravity case, what we do, since we cannot write the Hodge duality operator, we cannot use it, we use what is called the first order formalism for these fields. That is, we introduce a zero form Lagrange multiplier, for instance, for FAB, the field strengths of the gauge vector, and in such a way to be able to introduce the dynamics of these fields in a proper way, but remaining in this geometric framework without spoiling invariance, without spoiling, sorry, geometricity of the theory. And a further note on Hodge duality is the fact that there is some powerful extension. Let me write powerful. I don't know how to call it, an extension or a better generalization of the rheonomic approach, which is based on the use of integral forms. And I'm not an expert, but I would be, since it is an extremely powerful approach and an upgrade of, let's say, the rheonomic one, because in this framework, you can allow for the inclusion of the Hodge duality operator, since you are allowed to integrate over the whole superspace. That is something that you cannot do in the rheonomic approach. And these, for some references on this approach with integral forms, you can find some works by Antonio Grassi, Carlo Cremonini, Leonardo Castellani, who are experts on this topic. I see that there is maybe. Okay. Yes, maybe let me. Yes, we can have a short break, and then we can meet in 10 minutes. Let's say we can have this short break also for asking questions if you like. So.
Okay, thanks, Lucrezia. Thanks, Lucrezia. So, as Lucrezia said, please feel free to ask questions without any problem. Okay, I have a short question about a thing you said previously. You said that we can ignore variations of M4 in the soft group manifold, and so in some sense you're saying that there is not a dependence on the embedding of the four-dimensional manifold in the extended one, in the extended group manifold, and this is trivial to understand, so it happens everything or every time, or there are some other external conditions on this.
Well, it's not actually. It's not so trivial, in the sense that in this geometric approach, this is what happens. But we will see that in particular in the geometric approach to supergravity, this is something that will be allowed and induced by rheonomy, in the sense that this is allowed for pure gravity from the fact that you have invariance under diffeomorphisms and invariance under the group of general coordinate transformations. While for the case of supergravity, you will have that rheonomy induce. It offers a scheme of transformation relating different configurations on space-time and on superspace on the other end, which allows you to have a theory that is actually really independent from the manifold on which you integrate, from the hypersurface on which you are integrating. And obviously, in the case of supergravity, it will be a submanifold of a hypersurface embedded in superspace, since we are not able to integrate over the whole superspace.
Okay, thanks. So if there are other questions, please ask them. Just unmute yourself.
I would like to ask you which is the meaning of soft group manifold. I mean, something like the algebroid, since there is a dependence on the point, or something else. I don't know.
not, this is actually just soft because it is softened, let's say, with respect to the rigid structure that you have when you consider the vacuum. It means that from the point of view of your theory, let's say, this is, I think, not very mathematical language, but this is the way in which I visualize it. It's that you have a group manifold with a structure that is described at from a Lie group, and therefore from the corresponding Lie algebra. And this is what happens in vacuum. Then when you want to describe a theory, a dynamical theory, you have to go out of this vacuum. And that's the way in which you have to soften your manifold. That is why it's called soft group manifold, since you are detaching somehow from the vacuum configuration, from the Lie algebra structure, introducing non-vanishing curvatures. And so this term soft is to say that we are out of the vacuum, essentially, yes.
Okay, thank you.
You're welcome.
Are there other questions? Okay, so we can have just a few minutes break and then we will resume, let's say at 12:20. Okay, I think we can resume. So Lucrezia, please, if you're ready, go ahead.
Yes, thank you. Okay. Okay, now you can see the screen.
Yeah, now we can see. Thanks.
Lucrezia,
Yes.
can I ask you something?
Yes.
Could you please elaborate a little bit about the idea of factorization and the steps from the vacuum configurations to the dynamical one? Because I'm not so used to the group manifold formalism.
I will do it right now, just really for show you how you get factorization in this geometric approach, in the group manifold approach. Since what you want is to have a fiber bundle structure with Lorentz essentially being on the fiber, in order to have not spurious degrees of freedom in your theory, since we know that at the end the field is the only dynamical field. And so these commonly, when you don't consider the whole group manifold, you don't have problems with this. You just see that this is a consequence of the H invariance, of the Lorentz invariance of your theory, and of the fact that you are considering the differential forms of VA and omega AB, but you have that the integration is done on something that is already on a fiber bundle structure, on this base, on the Feldman basis. While on the other hand, in the group manifold, what you have, we will now see what happens. You can what you get is that the factorization is kind of dynamically implemented in this approach, and we see how. So this is good also because you understand which is the dynamical way of getting factorization, and also the geometric way in which you can conceive it. So we can start by writing the action, but which will look formally the same that we have written before for the Cartan formalism. But now what we have is that the integral of this integrand, that is the Lagrangian, is over this M4 embedded in G tilde, that is the soft group manifold, and M4 is an arbitrary surface immersed in G tilde, where G tilde, we recall, that is the ISO 13 soften. And also the equations of motion are formally the same, but now they are valid on the whole group manifold, since M4 is an arbitrary surface immersed in this G tilde. So UM valid on whole G tilde, since M4 is arbitrary. And then what you can do is expand the curvatures that appears in your theory. So most importantly, the Lorentz curvature, but also the torsion. You can expand them along a basis given by the Vierbein and spin connection, a basis of two form that is, let me write mu A, mu B, since these are the fields of our theory. And so the basis is given by V, B, V, B, omega A, B, B, C, and omega, omega. And this is the basis of the cotangent plane to G tilde at each point of M4. And after that, you can consider the projection of the equation of motion along, just along VA, VB. And from this sector, you get just the same equations of the Cartan original setting. While if you take those sectors with at least one omega, so from this other sector, you get that for the corresponding components, we have this solution, R, A, B, C, components along L, M, so along spin connection and Vierbein, equal to the component long spin connection, and the same for the torsion also, the A along the Vierbein and spin connection, and the A along spin connection are 0. So you get in a dynamical way from the study of the equation of motion, by exploiting the fact that now this is the basis that you have, you get that these components along at least one Lorentz direction, one spin connection, are 0. And so this is horizontality. Horizontality of the curvatures along the Lorentz subgroup. And in this way, we can say that G tilde is acquired dynamically a fiber bundle structure that is G tilde over H, H. And so this is the way in which factorization and horizontality emerge in the group manifold approach. In the present case, in particular, we have that G tilde is ISO 13 tilde and H is SO 13. The curvatures, and say that we have this fiber bundle structure that we have written before, is equivalent to say that the curvatures are horizontal. That is, that their components along the H directions find by the one forms dual to the generator of H, that is of the fiber vanish. And the advantage of defining the fields on the group manifold, considering space-time as a hypersurface immersed in G tilde, is precisely the fact that the factorization of Lorentz coordinates and the Lorentz invariance of the Lagrangian follows from the equation of motion in a dynamical way, in a dynamical theory on the fiber bundle. And in Sugra, supergravity, but also in gravity. At the end, what we know is that the Lagrangian is H invariant. By construction, we built the H invariant Lagrangian. So at the end, we don't see this mechanism of factorization. We don't implement it. We just assume H factorization from the very beginning, considering the H invariance Lagrangian on GTL over H. And then there is another observation that we can do regarding, again, invariances and transformations on these theories and this approach. That is the fact that this diffeomorphism acting in the direction orthogonal to space-time and can be interpreted in either in a passive or in an active way. So we can have both the passive and active points of view for diffeomorphism. And also this also maybe answer to the question previously asked by Carlo, in the sense that from the passive point of view, we have that diffeomorphism implement a lift from M to M4 prime, where we have the same theory, therefore M prime is the same theory, but in a different Lorentz frame. So we have that this lift correspond to a Lorentz transformation, and then we have that a diffeomorphism on the group manifold reduces to a Lorentz gauge transformation when the curvature along the Lorentz subgroup are horizontal. And on the other hand, from the active point of view, we have that we are restricting the Lorentz factorized theory to a fixed M4, that is a physical space-time. And the same diffeomorphism allows to consider the theory with, diffeomorphism allows to consider the theory with all possible Lorentz transformation. And another thing that we have to say is something regarding gauge transformations and diffeomorphisms in this context that is better to specify now. So let me now consider briefly gauge transformations and diffeomorphisms. And in particular, we show explicitly, in an explicit way, that the diffeomorphism reduces to a gauge transformation when the curvature are horizontal, while it differs by curvature terms in the general case. So we consider an infinitesimal element of the group of general coordinate transformation on GTL, and in particular we take a tangent vector on GTL, which we call T. It's given by epsilon m T m, where epsilon m is delta x m. And this M index label all the coordinate is a coordinate index on GTL. Then using the field band mu A that we have defined before and the whole set of on the supergroup manifold, we have that we can write this tangent vector as in terms of epsilon. Epsilon is equal tilde A with the tilde here on top, and therefore epsilon A here is the epsilon m mu A m, where epsilon A now is delta XA, and T tilde A now is T M mu M A. And this is an infinitesimal parameter of the shift, while this is the vector field generator dual to mu A, to our set of fields, so that is mu A T tilde B is equal to delta AB. And now in this setup, we can consider an infinitesimal generator of diffeomorphism generated by epsilon A. And we can write it as in terms of the derivative, that is, so infinitesimal diffeomorphism is the Lie derivative of mu A, which is given by the contraction along epsilon, the epsilon parameter of the derivative of mu A plus the derivative of the contraction along epsilon of mu A. And but then we can write that this is equal to this first term plus the derivative of the contraction along epsilon B T tilde B of mu A, that is in particular the contraction of the derivative of mu A plus this, that is the derivative. Since we take the contraction of mu A, we get precisely the derivative of the parameter. And then we can add and subtract 1/2 CABC mu B mu C to sorry, here there is an index that is A. Okay, we can add and subtract 1/2 CABC mu B mu C to this strata, to the mu A, and use also the definition of the covariant derivative. So epsilon is equal to the derivative of epsilon, ordinary derivative, plus C ABC. And so what we can do is that, recalling that the CABC is antisymmetric in BC, we can write the Lie derivative by using all of this information. Sorry. As the contraction of d mu A plus 1/2 CABC mu B mu C minus epsilon BC ABC mu C plus the derivative of epsilon. And so here we have exploited the definition of the covariant derivative of epsilon, the derivative plus epsilon CABC mu. And here we have added and subtracted this structure to get this, that is the curvature RA, and this, that is the gauge covariant differential precisely. And so at the end, we can write the expression for the Lie derivative of mu A as the derivative, the gauge covariant derivative of the parameter, plus the contraction along epsilon of the curvature. And then in this setup, we have that an infinitesimal diffeomorphism on the manifold G tilde is actually a G gauge transformation plus G gauge transformation plus these curvature correction terms. And in particular, if we have that RA, so the curvatures as have a vanishing projection along a vector, that is if RA has vanishing projection along, let me write epsilon b TB with tildes and so on, where B tilde is the adjoint index of the subgroup H contained in G tilde. Then we have that the contraction of the curvature, that is 2 epsilon B R A B C mu C is equal to 0. And therefore, this means that the action of the Lie derivative, in this case, the action of the Lie derivative L along the parameter epsilon coincide with a gauge transformation. That is essentially when we don't have this contribution, the Lie derivative coincide with a gauge transformation. And therefore, we recover horizontality of the curvatures along the H direction of the fiber bundle structure G over H, where over H, that is where G tilde over H is the base manifold, and H is the gauge group, gauge subgroup. And so this is to let you see how we have this relation between diffeomorphisms and gauge transformations on in this geometric approach. We see that the diffeomorphism differs essentially from a gauge transformation of the group by means of the presence of these curvature terms. And we can conclude that if the theory on G tilde can predict the horizontal curvature, so we have seen that also if we have the theory on G tilde, we can have horizontal curvatures, which leaves on G tilde over H. And this is therefore equivalent to the original curtain approach, but seen from the point of view of the whole Poincare group. And also that if we consider the Lie derivative of mu A, we get this given by the gauge transformation plus curvature correction terms. And this, again, here we don't have any explicit reference to the specific G tilde that we are considering. This is also for any group, including also supergroups, as we will see in the supergravity case. So now we can move, if there are questions, just ask. And then we can move to a brief overview for today of the geometric approach to supergravity. I will sketch you the key points of the geometric approach to supergravity. And then if I have time, I will also give you a brief review of n=1, n=4 pure supergravity on space-time, which is the toy model, the example that we are going to use to explain in detail the rheonomic approach and to see how it works. So let me move to an introduction, which I will deepen tomorrow on the rheonomic geometric approach supergravity. And first of all, we have to say that it's a superspace approach. And also, let me also mention that here we will consider from the very beginning the theory to possess a Venetian fiber bundle structure. And it will allow a geometrical interpretation of supersymmetry, analogous to the one that we have, analogous to the geometrical mechanism that we have for Lorentz factorization in gravity. And this will also happen in the rheonomic case, in the supergravity case, but we will see how in detail is analogous but slightly different. It has more things to take into account. And we will consider the example of n equal 1 equal for supergravity. The invariance of the supergravity Lagrangian will be due to the behavior of the supercurvatures along the fermionic components of the superfield in superspace. This will be different from what happens. This is what I meant before. It's different from what happened for, and will still happen for, the omega AB, so for the Lorentz directions. And for fermionic components, I will mean the fermionic components from here psi alpha, which is the gravitino, where alpha is a spinor indices. And what happens in this geometric approach to supergravity is that the dependence on the superfields on the other coordinates that we have in superspace, since in superspace we have already mentioned that we also have, besides the usual bosonic components, Lorentz, it is factorized, and we have these theta alpha that are the Grassmannian components. And so the dependence of the superfields on these other coordinates does not imply their complete factorization. And this is the key point in the supergravity. We have to find some way, and we will see that this happen, to allow us to have this physical content on superspace, on the superspace description that we actually have on space-time. That is, at the end, the possibility of restricting the theory from superspace to space-time. And such components are the components of the curvatures that will be, so the components that will be at least along psi direction of fermionic direction of superspace. Since here we will have the expansion along the superfield and basis, which is given by the A psi. So we will have VA, psi, V, and psi to expand the curvatures. And we will see that those components of the curvatures with at least one along at least one fermionic direction will be expressed in an algebraical way, linearly, as a tensor combination of the curvatures restricted to the bosonic cotangent plate of the space-time, of the embedded space-time hypersurface. That is on the purely bosonic VA, VB components, which span a basis on the cotangent space of ordinary space-time. And this is the way in which, in the rheonomic approach, we get rid of the unwanted degrees of freedom of the theory. Then we can insert this result in the Lie derivative formula that we have written before. And precisely this rheonomic principle, or these rheonomic constraints on the curvatures, on the components of the curvatures, will allow for a geometrical interpretation of local supersymmetry transformations. And this is actually valid for, I will focus on n equal 1, d equal 4, but this is actually valid for any supergravity theory in dimensions from dimension 4 to 11, and with an amount of supersymmetry charges from 1 to 8. where n is the number of supersymmetry generators in the Lie algebra, and also for pure metal couple theory. And it actually works also for rigid theories, or also in the case in which you want to study, for instance, a rigid theory on a curved background. And so before moving to superspace and to the geometric approach, I will just quickly review n equal 1, d equal 4 pure supergravity in space-time. While tomorrow we will see n equal 1, d equal 4 pure supergravity in the geometric approach in superspace. And I will also give you some other applications of the rheonomic approach. So in n equal 1, d equal 4 pure supergravity, we have any supergravity theories in general. We have local supersymmetry, which automatically implies gravity, and therefore we have a spin 3/2 field. This is psi mu. The gravitino is dual to the supersymmetry charge Q. And when we want to construct a gravitational, a supergravitational theory, in particular in n equal 1, d equal 4, we have to couple, but this is also for all supergravity theories, we have to couple the Raritas-Schwinger field, that is psi, to the Einstein gravity. And then we will write, therefore, a space-time action in the field in basis, which describes the coupling of the spin 2 graviton and the spin 3/2 gravitino. And this is the action for the present case. It's integral over M4 of RAB BC BD epsilon ABCD plus alpha, where now I'm just adding this free parameter, that is the coupling constant, and that is then fixed for consistency of the theory. Psi bar gamma 5 gamma A derivative of psi wedge B A. Though, where we have that gamma 5 and gamma A are the gamma matrices in 4 dimensions, and D is the Lorentz covariant derivative. In particular, the curvatures are defined in this way. We have, as usual, the Lorentz curvature. And the gravitational field strength, which I also call rho sometimes. So here I put just rho, is the psi equal, defined as derivative of psi minus 1/4 omega AB gamma AB psi. And this is the way in which the Lorentz covariant derivative acts on this fermionic field, on the gravitino. And now we have general for this action, we have general coordinate and Lorentz invariance, and moreover we have local SUSY invariance. And one can prove that if this parameter alpha is equal to 4, then we have invariance under local SUSY transformation, under local supersymmetry transformations. And let me write them in here in the second order formalism but you can also write them in the first order one. For me, this epsilon is the spinor parameter of local supersymmetry transformation, and the transformation of the Philben under supersymmetry is given by I epsilon gamma I psi. For the Gravitino, it's just the derivative, the Lorentz covariant derivative of this parameter, of this spin parameter. And for the spin connection, let me write it in this way. I also, yes, I also exploit a coordinate index. In this way, from the Philben, and then we have the supersymmetry parameter, gamma mu derivative of psi, and then minus the other combination, so epsilon bar, gamma rho, mu psi mu. And these are the local SUSY transformations, supersymmetry transformations of the fields. And then we can come back to the action. Let me move here just to tell you which are the terms that appears here. So we have said that here we have a 4, and this is the Einstein-Hilbert term that we have already seen, while this other one is the so-called Rarita-Schwinger term. And now we can study the equation of motion of this action. And so we vary again with respect to the, again, alla Palatini, let's say, we vary with respect to the spin connection, to the Philben, and to the Gravitino field. From the variation with respect of the spin connection, we get to RC VD epsilon A, B, C, D equals zero, where now we have this object that is the super torsion to form, and is defined as RA, the covariant derivative of the Philben minus 1/2 psi bar gamma A psi. And we can see that this in fact differs from the torsion, from the purely bosonic torsion, since here we also have the fermionic directions of superspace. And this equation can be manipulated in the same way in which we have done for pure gravity. We get that R A M N equals 0. And then we will see also that the torsion, we will see this tomorrow actually, but that the parameterization of the torsion on superspace in this case doesn't have components along the fermionic direction, but just along the bosonic ones. And therefore, this implies that the super torsion is equal to 0. And yes, in fact, this is different from the torsion for 2 reasons. This is the super torsions. First, because we have the fermionic components here. And also, and second, for the fact that now we have to consider all fields and curvatures expanded along the super Philben basis. Yes, sorry, no, sorry, I get confused. This, yes, is for the rheonomic approach. Here in this case, we are on space-time, so this is what will happen in the rheonomic approach, in the sense that we will have to expand along the whole super Philben basis, but the torsion, we will see that we'll just have purely bosonic components. While here, obviously, yes, we are on space-time, so these are the only components of the super torsion, and so this equation implies that the super torsion is 0. And we can observe, that omega AB here is a non-Riemannian connection, since it is actually the super torsion that vanishes and not the torsion. So the derivative of A that was the torsion is different from 0. And then again, from this equation, we can exploit it to write the spin connection in terms of the field bane and its derivatives and of the gravitino. And in this way, we have that we don't have extra degrees of freedom in our theory, no spurious degrees of freedom. And this condition, RA equal 0, is also called as the on-shell condition. Condition for the connection. And if you implement it from the very beginning, you are working in the second order formalism. While if you consider it different from 0 from the very beginning, and then okay, you get that it is on shell 0, but you consider it different from 0 from before varying the action, you are working in the first order formalism, where the spin connection and the field band are independent a priori. And then from the equation of motion, you get that the spin connection is given by the field band in terms of the field band and gravitino. And I will adopt in this short review the second order formalism. So let me now write the variation of the action from the equation that we get from the variation of the action with respect to the field bane. We get this equation. And we can prove that this is formally the same as in pure gravity, but now the spin connection is different, since we also have that the fermionic components appear into the fermionic fields appear into the expression for the spin connection. And then from the variation with respect to the gravitino, we get 8 gamma 5 gamma A derivative of psi VA equals 0. And one can prove that the equation of motion of the field band produces precisely the expected interaction between the field band and the gravitino. And moreover, for this equation, we have the same thing, plus the fact that we have a self-interaction of the gravitino field, so with itself. So we have consistency coupling of the Rarita-Schwinger field of psi to gravity in this Lagrangian. And this is what suggests the existence of an extra symmetry that extend the gauge invariance of what would be the free field spin 3/2. And so this is extended to the interacting case indeed, and this extra symmetry is in fact supersymmetry. And now what we have is invariance under local Lorentz transformation, invariance under diffeomorphisms, and one can also define a suitable SUSY transformations leaving the Lagrangian invariant and representing the SUSY algebra that is on the on-shell state. And in fact, we have that SO13 is an off-shell symmetry of the theory, while on the other hand, supersymmetry is a non-shell one in the sense that it closes only, on the equations of motion. Then since SUSY algebra closes only on the equation of motion. And then we can compare the supersymmetry transformations that we have written before for our fields with the gauge transformations of the supersymmetry derived from the super Poincaré algebra, so from the whole gauge transformation of the super Poincaré group. And what we get is that they are different in this sense, and this is one of the last thing that we see today, because I'm slightly out of time. So let me rewrite the supersymmetry transformations of our theory. We have this one for the Vierbein. This one for the Gravitino. It is the derivative of the parameter. And epsilon is the spinor. SUSY parameter. And then the one for the spin connection in the second order formalism. I'm just rewriting the expression I wrote before so that you see the comparison with between the supersymmetry transformation and gauge transformation of the super Poincaré group. Okay, and then we have the gauge supersymmetry transformation, that is the one associated with the super Poincaré group. And these are, for, let me denote them with this label gauge. For the Vierbein, we have that they coincide with the supersymmetry transformation, as we can see, they coincide. Then for the Gravitino, again, we have that they coincide, and this can be written starting, for instance, from the Maurer-Cartan equation of the theory and taking contraction. So again, we see that for gauge, let's say supersymmetry, so based on for the transformation, for the gauge transformation of the super Poincaré group, again, this coincides for the Gravitino. But finally, for the spin connection, what we get is that the gauge transformation is 0, and therefore it is different from the supersymmetry, from the local supersymmetry transformation we have written before. And also, we can notice that this one for the Gravitino resembles a gauge transformation of a gauge field. So the way in which we have written here, the supersymmetry transformation resembles the gauge transformation of a gauge field, but this is actually due only to the fact that we are considering a very simple model that is n equal 1, d equal 4 pure supergravity without matter, while this will be different in more complicated models. So these differences between SUSY transformations and gauge supersymmetry transformations would be more manifest also in other sectors and not only in the transformation of the spin connection. And so we can conclude that local SUSY transformations leaving invariant the action are not gauge supersymmetry transformations. And this is a subtlety actually, because commonly we say that I've already heard that supersymmetry is the gauge symmetry of supergravity, or that supergravity is the gravitational theory of gauge supersymmetry. While okay, we have to be careful to what we mean by gauge. In the gravity case, okay, we can just reduce this use of the term gauge in this sense, and but yes, in fact, actually, local supersymmetry is not gauge supersymmetry transformations, and this is analogous to what happened in pure gravity, when we have that the action is not invariant under gauge translations again. Also, if sometimes we say that we have, for instance, also in an example that we will see, a conformal theory for gauge supergravity. Okay, it's not actually gauge supergravity, but since we have invariance not under translation, but invariance against the diffeomorphisms. And under diffeomorphisms, the connection transforms, as we have seen with the derivative, and the two so gauge translations and diffeomorphisms differ on essentially on the spin connection. And moreover, we have that supersymmetry transformation clause on shell with structure function, as we will see. Rather than with structure constants, as it would be for a genuine, let's say, gauge transformation. And so gauge translation leaves the psi, the gravitino, inert. And then we will see tomorrow the way in which the on-shell supersymmetry algebra emerges as the algebra of diffeomorphisms in superspace. In particular, a supersymmetry transformation in superspace, so in the geometric approach to supergravity in superspace and not on space-time, will be a diffeomorphism in the fermionic direction of superspace. So, okay, I think that for today it's we are fine, and if you have a question, just ask.
Okay, thank you very much, Lucrezia. Is there any question? Okay, actually, I have one question. And in a general rheonomic theory, are there conditions that assure me that a priori that supersymmetry can close off shell instead on the equation of motion?
Yes, okay, yes, in fact, when I say that supersymmetry, thank you, Carlo, for this question, because otherwise it would have been unclear, in the sense that I say that, yes, it's true, supersymmetry closes only on shell on the equations of motion, but this is not the case, with the exception of the case in which you have auxiliary fields on your theory. You introduce auxiliary fields in the theory, and you can also obviously study supergravity in the rheonomic approach by adding auxiliary fields in your theory. And what you will have is that supersymmetry will be allowed to close off shell. And in particular, what you have is that this will also have repercussions on the Lagrangian of the theory. In particular, you can prove that the exterior derivative of the Lagrangian in the presence of auxiliary field automatically vanishes. And but yes, I was here. I don't consider the presence of auxiliary fields, so I will always say that we refer to on-shell supersymmetric structures. And yes.
Okay, thank you very much.